Settle in. Let your body find its place against the mattress. The bed gives beneath your weight in a way that feels familiar, earned. The blanket rests over your chest, warm and steady. The pillow is cool against your cheek, and for a brief moment that coolness feels like the simplest pleasure in the world. Outside, the world is still moving, but not for you. A distant car passes. A faint rush of wind slips through something unseen. Maybe there's the low murmur of a television somewhere beyond your walls. None of it asks anything of you. None of it needs a response. Your breathing begins to slow. You don't decide to do this. It just happens. The nervous system shifting gears, muscles softening, the invisible work of holding yourself upright all day quietly coming to an end. Your thoughts are loosening now, not gone, just less solid. A conversation fragment, an unfinished task, a face, an image that doesn't fully belong to anything. You are not asleep, but you are no longer fully here either. And then, you hear it, your name, spoken clearly, not loud, not distorted, just there, the exact shape of it, the way it sounds when someone who knows you says it, close enough to feel personal, real enough to make your heart tighten for half a second. Your eyes open. The room is empty. The air hasn't changed. The walls are still. No footsteps. No second presence. And yet your brain was certain. For a moment, it believed someone had called you. Tonight, we're gonna stay inside that moment and explore why the mind sometimes speaks in a voice that feels like it isn't its own. The most familiar sound in the world. You've heard it before, maybe more than once. Maybe it happens to you regularly, and you've never quite known what to do with it, just chalked it up to exhaustion or an overactive imagination, or that vaguely unsettling category of things that happen to you right before sleep that don't quite have a name or an explanation. That voice, your name in the quiet, the feeling of being called by someone who is not there. If you have experienced it, you know the particular quality of it. You know how it doesn't feel like a dream. It doesn't have the soft, hazy texture of a dream, where the edges blur and the logic bends and everything feels slightly distant or underwater or somehow beside the point. Dreams have a texture that you recognize, even in the middle of them, a quality of the possible becoming elastic, of rules gently releasing their grip. This is not that. This is sharp. This is clear. This is a voice in the room with you, and it spoke your name, and for a moment every sleeping part of you lurched back into wakefulness because something very old and very deep inside you registered. Someone is here, and they are calling for me. And then there's the return to stillness, the gradual realization. The room is dark. The house is quiet. The door is closed. There is no one. If you haven't experienced it, you may have experienced something adjacent to it. A sound that wasn't there. A word spoken into silence that made you jolt yourself awake, convinced you'd missed something important, some summons you'd failed to answer. A fragment of music from no discernible source. A phrase in a voice you couldn't place. All of it is the same family of phenomenon. All of it lives in the same remarkable neurological territory. And all of it, when you understand what is actually happening, is evidence of something profoundly interesting about what it means to have a human brain. Before we get there, before the science, I want you to sit for a moment with the experience itself. Because one of the things that gets lost when we move too quickly to explanation is the genuine strangeness and intimacy of what this is. Hearing your name, Of all the sounds the brain could generate, of all the things it could produce in the quiet before sleep, it chooses this. The sound that has been the most consistent accompaniment to your existence since your earliest days. The sound that has meant, in 1,000 different voices and 1,000 different contexts and across the entire arc of your life. You are here, you are seen, and someone knows your name. There's something in that worth sitting with. We'll come back to it. But right now, let's start with the science. What you are experiencing in those moments before sleep is called a hypnagogic hallucination. The word hypnagogic comes from the ancient Greek, from hypnos, the god of sleep, and agoagos, meaning a leader or conductor, the conductor of sleep, the one who guides you across the threshold. Hypnagogic hallucinations are perceptual experiences, sounds, images, sensations that occur in the transitional zone between wakefulness and sleep. They are common. Multiple large surveys of the general population have found that somewhere between 25 and 70% of people experience them at some point in their lives, depending on how strictly the researchers define the experience and how carefully they asked about it. The range is wide, which tells you something important. These are not rare events that happen to a small number of unusual people. They are widespread. They are normal. They are, in fact, one of the most ordinary, extraordinary things that the human brain does. Up to 70%. Which means that if you're watching this with someone right now, which, given that this is a sleep channel, you probably aren't, but hypothetically, there's a better than even chance that both of you have lain in the dark and heard something speak out of the silence. And yet, almost nobody talks about it. Almost nobody knows what it is. It lives in that category of personal experience that is common and private simultaneously. The kind of thing you might have mentioned once hesitantly to someone you trusted and then worried slightly about their reaction. The kind of thing that makes you wonder briefly if something is wrong with you. There isn't. There is not a single thing wrong with you. And tonight, we're going to understand why not only is this experience completely normal, but it is evidence of some of the most sophisticated and ancient neural architecture your brain possesses. We're going to understand why this happens in detail with the actual neuroscience. We're going to trace the experience from the first moment of the hypnagogic transition all the way through the specific circuits that generate voices, and then we're going to understand the most specific and fascinating piece of all. Why your brain, of all the sounds in its vast acoustic library, so often chooses to generate this one. Your name, spoken in the dark. This is the story of a brain that never fully stops listening. A brain that is still, even in the deepest moments of rest, running its most ancient and most personal program. And a brain that, in the strange liminal space before sleep, sometimes says the most important thing it knows out loud into the quiet. The territory between worlds, what N1 sleep actually is. To understand why your brain generates voices in the dark, we first need to understand what is happening to your brain in the exact moment when they appear. Because the voice before sleep doesn't come from just anywhere in the night. It comes from a very specific place in the architecture of sleep, a very specific transition point, a particular neurological territory that lasts only minutes but is, in those few minutes, one of the most remarkable states the human brain ever occupies. Sleep is not a single thing. It is easy to think of it that way. To think of sleep as simply the opposite of waking, the brain's off switch, the absence of experience. But this is completely wrong, and sleep researchers have known it for decades. Sleep is a dynamic, structured, elaborately choreographed sequence of states, each governed by different brain chemistry, different electrical patterns, different physiological processes, and different relationships between the mind and the world around it. Scientists have been able to map these states with extraordinary precision using a technology called the electroencephalogram, or EEG. Invented in the 1920s by the German neurologist Hans Berger, the EEG works by placing small metal electrodes, sometimes in a cap, sometimes glued individually to the scalp, on the surface of the head. These electrodes pick up the faint but measurable electrical fields produced when large populations of neurons fire together. The result, when you look at the readout, is a running record of the brain's electrical life. A waveform that rises and falls in patterns that are specific, consistent, and deeply informative. What the EEG reveals when you attach it to a person and watch them fall asleep is that the brain does not simply go quiet. It changes, systematically in a specific sequence, in a way that is remarkably similar across all healthy humans. When you are wide awake and mentally engaged, reading, thinking, having a conversation, doing anything that requires focused attention, your brain is dominated by electrical oscillations that researchers call beta waves. These oscillate at roughly 13 to 30 cycles per second, which is the unit we call hertz. 1 cycle per second equals 1 hertz. Beta waves are fast, relatively low in amplitude, and somewhat irregular. They are the electrical signature of a brain that is actively engaging with the world, processing information, maintaining attention, executing thought. As you relax, as you lie down in the dark, as you close your eyes, as the stimulation of the world recedes, the beta waves begin to slow and give way to something gentler. What emerges are alpha waves, oscillating at 8 to 13 hertz. Alpha waves have a beautiful, rhythmic, almost wave-like regularity that beta waves lack. They are larger in amplitude. They are smoother. They are the electrical signature of a mind that is at rest but still awake, calm, unfocused, gently turned inward without being asleep. Alpha waves are associated with states of relaxed but present awareness. The meditative state that many people describe, not asleep but not fully engaged with the outside world, floating in a kind of pleasant internal quiet, tends to be rich in alpha activity. Researchers in biofeedback and meditation science have studied alpha waves extensively, and the consistent finding is that deliberately increasing alpha activity feels good, relaxing, pleasant in a way that is distinct from both the alertness of wakefulness and the blankness of sleep. If you've ever lain down at the end of the day and felt that particular quality of being deeply, luxuriously, thoroughly relaxed without being asleep, the feeling of all the tension draining out while the mind drifts without direction, that is, broadly speaking, an alpha state, and it is usually where the journey towards sleep begins. But the alpha state is not sleep. It is the antechamber of sleep. It is the waiting room, as you continue to drift. As the minutes pass and the darkness deepens and your body temperature gently drops and the physiology of sleep onset begins to assert itself, the alpha waves begin to give way to something slower still. Theta waves, oscillating at 4 to 7 hertz. Theta waves are larger, slower, more irregular than alpha. They represent a brain state that is genuinely different from anything in ordinary wakefulness. They are not just a slower version of alpha. They are a different mode. The transition from alpha to theta marks the beginning of what sleep researchers call stage N1, the first and lightest stage of non-REM sleep. This is the official, formal beginning of sleep. And it is in N1 sleep, in the theta-dominated haze of this earliest stage, that hypnagogic hallucinations occur, and one sleep is brief, typically lasting somewhere between 1 and 7 minutes, though this varies considerably from person to person and from night to night. By the standards of the sleep architecture that follows it, it is extraordinarily short. Stage N2 sleep, which comes next, lasts roughly 20 to 30 minutes per cycle. Deep N3 sleep, what used to be called slow wave sleep, lasts 30 to 40 minutes, particularly in the first cycle of the night. REM sleep, where most vivid dreaming occurs, can last anywhere from 10 minutes in the first cycle to 45 minutes or more in later cycles. These are substantial stretches of time. And one is not substantial. It is a doorway, not a room. But in those few minutes, extraordinary things happen. The muscles of the body begin to genuinely relax. Not just the voluntary relaxation of lying still, but an actual reduction in muscle tone that is governed by the nervous system's sleep onset programming. The eyes, beneath their closed lids, begin to move in slow, rolling patterns. Not the rapid, darting eye movements of REM sleep that come later in the night, but a slow, dreamy rolling that is one of the earliest signs that a person has crossed from resting wakefulness into actual sleep. Heart rate slows. Core body temperature drops by about 0.5 degrees Celsius. The brain begins actively changing what it is doing. And in N1 sleep, something happens to the way the brain handles information from the outside world that is central to everything we're exploring tonight. During N1, the boundary between the mind's interior world and the sensory world outside becomes profoundly, almost startlingly permeable. The systems that normally manage this boundary, the systems that keep your perceptions organized and reality tested and correctly attributed to their actual sources, begin to stand down. The careful mental machinery that says that sound is a car on the street, or that flicker of color is just the street lamp through the curtains, or that voice is coming from the television in the next room, not from inside this room. That machinery begins to step back from active duty. And in the space that machinery leaves behind, the brain begins to do its own thing. Unconstrained, unmonitored, generative in a way it can never quite manage when the rational mind is fully in charge. This is hypnagogia, the threshold, the conductor's country, the brain in its most extraordinary, most boundary-dissolving, most genuinely strange state. And in this state, in N1 sleep, in the drowsy theta-dominated haze of the first few minutes of sleep, two processes are happening simultaneously that normally don't happen together. On one hand, the brain is still receiving information from the outside world. The ears are still working. The auditory system is still processing the sounds of the room, the house, the night. The external world is still feeding data into the system. On the other hand, the brain's internal generative machinery, the systems responsible for imagination, memory, dreaming, and the construction of inner experience, has begun to activate. Internal images arise. Internal sounds surface. The brain starts producing its own content, unbidden and often unexpected. And crucially, this is the key. The brain can no longer clearly tell the difference between what is coming from inside and what is coming from outside. In N1 sleep, internally generated content can feel external. And external information can trigger internal elaborations that feel completely real. This confusion of origins is not a glitch. It is not an error in the system. It is what happens when the brain's normal reality monitoring infrastructure is partially offline. It is the predictable result of a specific neurological state. And it is precisely where the voice comes from, the brain that never stops listening. Here is something that might surprise you, and it surprised the neuroscientists who first found it, too. Your auditory system does not fully shut down when you sleep. For a long time, the assumption about the sleeping brain was relatively simple. Sleep is a state of reduced responsiveness to the environment. The sleeping person doesn't react to most sounds. You can have a conversation at normal volume next to a sleeping person and they won't wake up. They won't respond. They won't even turn over. Therefore, or so the reasoning went, the brain must be blocking sensory input at the entry point. The gate must be closed. The signal is being intercepted before it can cause a response. It was a logical inference, and it was, as it turns out, not quite right. The more researchers looked, using more sophisticated methods and more direct measurements, the more complicated the picture became. The sleeping brain is not simply cut off from sound, continues to process it, not identically to the waking brain, and not with all the downstream consequences that waking processing has, but in a manner that is considerably more sophisticated and more similar to wakefulness than the simple gate-closed model would predict. Some of the most compelling evidence comes from studies using intracranial electrodes placed directly on or within the brain tissue itself, rather than on the scalp. This gives a much more direct and detailed view of what individual neurons and small populations of neurons are actually doing, without the spatial blurring and signal degradation that affects scalp EEG. Studies published in journals including Nature Neuroscience have used this approach to record from the auditory cortex of patients during natural sleep, and the findings are striking. Research published in Nature Neuroscience in 2022 by Yuval Nir and colleagues found that when sounds were played to sleeping participants, auditory cortex neurons fired robustly, with high gamma activity, which is the kind of fast, fine-grained neural activity associated with active information processing. The magnitude of these responses was only moderately reduced from wakefulness. The early auditory cortex was doing something when it heard sounds during sleep, and it was doing something that looked meaningfully similar to what it does when fully awake. What differed was what happened downstream. The feedback processes, the alpha and beta wave activity that in waking reflects the brain's higher-level processing and interpretation of what it's hearing, were strongly reduced during sleep. The bottom-up sensory response remained largely intact. The top-down interpretive and feedback process was diminished. What this tells us is something beautifully specific. The brain's primary hearing machinery, the part that processes the physical features of sound, that detects patterns, that runs the raw data, is operating during sleep in a way that is much closer to wakefulness than we realized. What's reduced is the interpretive overlay, the top-down processing, the flow of information back from higher cortical regions to sensory cortex that helps interpret what the sensory cortex is detecting. In other words, the sleeping brain hears. It just can't fully make sense of what it hears, and it doesn't fully broadcast what it hears to the rest of the conscious system. But the hearing, the initial processing, that is very much alive. An earlier landmark study by Christoph Portis and colleagues, published in the journal Neuron in 2000, used a combination of fMRI brain scanning and EEG to track what happened in sleeping human brains when they heard various sounds. The auditory cortex, the thalamus, and the caudate nucleus all showed activation when sounds were played, both during wakefulness and during NREM sleep. These regions were activated by sound regardless of whether the person was awake or asleep. The difference was in the frontal and parietal regions, the areas associated with conscious attention, working memory, and higher-level interpretation, which were less strongly activated during sleep. And then came the finding that is most directly relevant to us tonight. When participants heard their own name during sleep, the left amygdala and left prefrontal cortex showed greater activation than when they heard a neutral or unfamiliar name. The brain, during sleep, was not merely processing sound in a generic way. It was distinguishing between sounds based on their personal significance. It was treating the sound of one's own name differently. The sleeping brain knows its own name, and it cares. Let's stay for a moment with the architecture of this auditory system, because understanding how it is built helps explain why it behaves the way it does. Your auditory system begins at your ears, specifically at the tiny sensory cells inside your cochleae, the snail shell-shaped organs in your inner ear. These hair cells transduce the mechanical vibrations of sound waves into electrical signals that travel along the auditory nerve into the brainstem. From the brainstem, the signal travels through a series of relay stations: the cochlear nuclei, the superior olive, the inferior colliculus, climbing upward through the hierarchy of the auditory system toward the thalamus. The thalamus receives the auditory signal and forwards it via what are called the medial geniculate nuclei, the thalamus's specific relay stations for hearing, up to the primary auditory cortex, also called a 1. A 1 is located in the upper part of the temporal lobe, in a region called Heschel's gyrus, and it is organized tonotopically, meaning that neurons in different parts of a 1 are tuned to different frequencies of sound. Low frequencies are processed on one side, high frequencies on the other, with the full range of human hearing mapped across the structure in a precise gradient. It is, in a sense, a map of sound drawn in neurons. From A1, the signal radiates outward to surrounding areas called the secondary and association auditory cortices, the belt and parabelt regions. These areas are where the real work of auditory perception happens. They extract patterns. They identify phonemes, the individual building blocks of speech, and assemble them into words. They recognize voices. They track the prosodic structure of language, the rise and fall of pitch that signals whether someone is asking or telling, whether they're anxious or calm, whether the word ending with that upward lilt is a question or a kind of pleading. They identify emotional content in speech. They connect what they hear to memories of similar things heard before. These areas, the association auditory cortices, are the places where a sound becomes meaningful, where the wave of air pressure becomes, "Someone said my name." And it is these areas, the research shows, that remain particularly active during the transition to sleep. Not as active as during engaged wakefulness, but far more active than the simple gate-closed model would suggest. There is a 2020 study published in the Journal of Neuroscience by researchers including David Schulz and colleagues that recorded simultaneously from both the primary auditory cortex and the parietal cortex, a downstream association area, in freely sleeping animals. They found that while the primary auditory cortex showed relatively modest reductions in response to sounds during sleep, roughly 10% reduced from waking, the parietal cortex showed much stronger attenuation, roughly 47% during NREM sleep. This gradient, strong responses in early sensory cortex, weaker responses downstream, tells us something precise about how the sleeping brain handles sound. The raw auditory processing continues relatively intact, but the signal doesn't propagate as fully or as richly through the wider network. But there's a critical exception to this pattern of downstream attenuation. And it's the exception that matters most for us tonight. When a sound is personally significant, when it carries emotional weight, when it has a history of importance, When it is the kind of sound that has reliably demanded a response, the downstream networks activate more strongly. The amygdala, which is sensitive to emotionally significant stimuli, responds more to personally meaningful sounds than to neutral ones, even during sleep. The prefrontal regions associated with self-referential processing respond more to your own name than to other names. The sleeping brain doesn't treat all sounds equally. It applies a personal filter, and certain sounds, certain specific, individually meaningful sounds, cut through the filter in a way that others do not. Your name is one of those sounds. And right now, even as you lie in the dark and feel yourself softening into sleep, some part of your brain is still out there listening, still scanning, still watching the soundscape for that one particular pattern that has always meant something important. The gatekeeper and its deliberate gaps, thalamic sensory gating. To fully understand what happens to sound during sleep onset, we need to spend some time with one of the most important and most underappreciated structures in the brain. A structure that sits at the center of your head, roughly at the level of your ears, like a hub around which the rest of the brain's sensory experience turns. The thalamus. The thalamus is a paired structure, two ovoid masses of gray matter, one on each side of the midline, connected by a small bridge of tissue called the massa intermedia. It is about the size of a walnut, and it is dense with neurons arranged in dozens of specialized nuclei, each with a specific function. Some of these nuclei relay motor information from the cerebellum and basal ganglia to the cortex. Some relay information about pain and temperature. Some are involved in attention and alertness. But the ones most relevant to our story tonight are the sensory relay nuclei, the ones that sit between your sense organs and your conscious experience of the world. Almost everything you perceive from the outside world passes through the thalamus on its way to the cortex. It is the most literal gateway to consciousness for sensory experience. The lateral geniculate nucleus relays visual information from the eyes. The medial geniculate nucleus relays auditory information from the brainstem. The ventral posterior nucleus relays touch, pain, and temperature from the body. These nuclei are the relay stations, the middle managers of the sensory hierarchy, receiving signals from the periphery and forwarding them to the appropriate cortical regions. But the thalamus, as I said before, is not a passive relay. It filters, it gates, it decides, based on the state of the organism and the relevance of the information, how strongly and how fully to pass signals on to the cortex. The mechanism of this gating lies in a remarkable structure called the thalamic reticular nucleus, or TRN. The TRN is a thin shell of neurons that wraps around the outside of the thalamus like a rind around a piece of fruit. Unlike most thalamic neurons, TRN neurons are entirely inhibitory. They use the neurotransmitter GABA, gamma-aminobutyric acid, which is the brain's primary brake signal, to suppress the activity of the relay neurons they surround. When TRN neurons fire, they inhibit the relay neurons. And when relay neurons are inhibited, they pass less information to the cortex. During wakefulness, the TRN is relatively quiet. The relay neurons are free to pass sensory information richly and fully to the cortex. The gate is open. You have the full, high-fidelity, information-rich experience of being awake. As you fall asleep, this changes. The TRN becomes more active. It begins to fire more, inhibiting the relay neurons more strongly, passing less information from the sensory world to the cortex. The gate begins to close. This closing of the thalamic gate is one of the fundamental mechanisms of sleep. It is why you stop responding to most of the sounds of the night. It is why the room can be the same room with the same sounds, and during the day those sounds feel vivid and present, and during sleep they become irrelevant. The thalamus has changed its filtering, and the sensory world is reaching your cortex with much less force. One of the most visible signatures of this gating in action is the appearance of sleep spindles in the EEG. Those characteristic bursts of rhythmic electrical activity at 11 to 15 Hz that emerge during stage N2 sleep, each lasting 1 to 2 seconds, looking like little spindle-shaped bursts against the background of slower waves. Sleep spindles are generated by the interaction between the TRN and the thalamocortical relay circuits it modulates. They represent cycles of inhibition, moments when the TRN is actively suppressing the relay neurons, and the thalamocortical circuit is oscillating as a result. Each spindle is, in a very real sense, the gate slamming briefly shut. Research has shown that sleep spindles have a functional role in protecting sleep from disruption. Studies measuring how much sensory stimulation is required to wake a person during different sleep stages have found that the N2 stage, when spindles are most abundant, requires more stimulation to produce an awakening than N1. The spindles are doing their job. They are keeping the outside world outside. They are holding the boundary that lets sleep deepen and persist. But, and this is crucial, the gate does not close completely. And for sound, specifically, the gate closes less completely than for other senses. There is something like a structural exception built into the system. Multiple lines of research comparing the residual sensory processing during sleep across different modalities have found that auditory processing is unusually resilient. While visual responses essentially disappear when the eyes are closed, and while somatosensory responses to touch diminish substantially, auditory responses in the primary cortex remain robust at magnitudes much closer to wakefulness than you might expect. The reason is almost certainly evolutionary. Hearing is the sense that guards the sleeping organism. The eyes close when you sleep, vision is unavailable. Touch requires contact. Smell is limited in range and typically can't detect threats from the distance that matters most. But sound travels through darkness, through walls, across distance. Sound carries information about things happening in your environment that you cannot see and might desperately need to know about. A branch breaking under the weight of something large. Water rising somewhere it shouldn't be. A child calling out in distress from another room. The crack of a fire starting. The mammalian lineage that carried forward into modern humans spent most of its evolutionary history in environments where the costs of sleeping too deeply were potentially fatal. The brain that allowed itself to be completely sealed off from the acoustic environment during sleep was a brain that might not wake up again. The brain that maintained some degree of auditory vigilance, even at the cost of slightly lighter or less efficient sleep, was the brain that survived to pass on its genes. So the thalamic gating system was shaped over millions of years to be deliberately and selectively leaky when it comes to sound. Not all sounds, not the background hum of the environment, not the steady, repetitive, familiar acoustic landscape of the sleeping space. Those are appropriately filtered and suppressed. But novel sounds, unexpected sounds, sounds that carry information about change or danger or personal significance, those pass through the filter with preferential ease. A key study from researchers including Matthias Eisen and colleagues and work from the laboratory of Jan Born have examined how the sleeping brain treats sounds differently based on their relevance. The brain does not apply its auditory filter uniformly. It applies it selectively, with the filter settings being calibrated through learning and experience to what kinds of sounds have historically mattered to the individual. The sounds that have reliably required a response, the sounds that have carried important information, the sounds that have been consistently linked to the need for action. These clear the thalamic filter more easily than sounds that have always been safely ignorable. Your name is the most extreme example of a sound that has reliably required a response. Every time you have ever heard your name in your entire life, there was an expectation that you would respond. Attending, acknowledging, turning toward the source. Your name has been the single most consistent signal in your acoustic history that something was being directed at you specifically, and that you needed to engage. The thalamic filter, shaped by all of that experience and history, has been calibrated to treat your name as a high-priority signal, one that clears the gate. And so even as you lie in the dark, even as the gate is closing, even as the theta waves of N1 sleep roll slowly across your brain and the spindles begin to form in the deeper stages to follow, even then, the auditory system maintains its vigilance. The channel for your name remains open. Your name above all others, a neuroscience of the self in sound. Your name is not just a word. I need you to hear that as more than a metaphor, because it is a literal neurological fact. Your name occupies a unique position in your brain's processing hierarchy, a position that no other word, no other sound, no other auditory stimulus holds. It is special in ways that are specific, measurable, and reproducible in laboratory conditions. And understanding exactly how and why it is special is the heart of what we're exploring tonight. Let's start at the beginning, your very beginning. You began hearing things before you were born. The auditory system develops enough to begin processing sound by around 24 to 26 weeks of gestation. For the remaining months of pregnancy, the developing brain is absorbing the acoustic environment, muffled and transformed by the layers of tissue and fluid between it and the world, but present. The sounds of the mother's voice are particularly loud and clear, because they are conducted through bone and tissue as well as through air. Research using measures of fetal heart rate and movement has shown that fetuses respond differentially to their mother's voice versus other voices well before birth. The mother's voice is, quite literally, the first voice the brain learns. After birth, the learning accelerates. In the first weeks and months of life, the infant brain is immersed in language at a pace that it will never quite match again. It is absorbing phonemes, the building blocks of the particular language or languages being spoken around it, and it is absorbing the acoustic structures of speech, rhythm, prosody, the patterns of stress and melody that distinguish one kind of utterance from another. And through all of this acoustic learning, one word stands out. One sound is repeated with more frequency, more consistency, more emotional weight, and more direct interpersonal significance than any other. That sound is the infant's name. Parents say their child's name constantly. They say it when they are looking at the child, which means the name is always paired with face-to-face connection, with eye contact, with the kind of social attention that the infant brain has been specifically shaped to register and value. They say it when they are calling the child, when they are soothing the child, when they are delighted by the child, when they are concerned for the child. The name threads through every emotional register from joy to fear. It is the one sound that is almost always, in every context, directed specifically at the infant. It means, this utterance is for you. By 4 to 5 months of age, infants reliably orient toward their own name when they hear it, even when they don't yet orient toward other words. This is not just a conditioned response in a narrow sense. It is evidence that the infant brain has already begun to develop specialized processing for this particular sound. The name has already acquired a neural significance that other words have not yet earned. This specialization deepens across the entire course of development. Your name is spoken to you thousands, eventually tens of thousands, of times in the first years of life. Each repetition strengthens the neural connections associated with that sound. Each emotional context in which it appears, affectionate, urgent, delighted, cautionary, adds layers to the emotional valence of the word. Each time it is used to get your attention, to direct social interaction toward you specifically, the brain's association between this sound and the concept of personal relevance becomes more deeply established. By adulthood, your name has been spoken to you more times than almost any other word you have ever encountered. It has been spoken by your parents, your siblings, your teachers, your friends, your colleagues, your doctors, your lovers. Every person who has ever known you has said it. Every significant moment of your life has been accompanied, at some point, by the sound of it. It is woven into the neural fabric of your identity at a depth that approaches the literal definition of what your identity is. And all of that history has neurological consequences. The most famous demonstration of the special status of your own name in auditory processing is a phenomenon that psychologists have studied since the 1950s, called the cocktail party effect. The name refers to something that most people have experienced and found difficult to explain. The ability to hear your own name spoken on the other side of a noisy room, in a conversation you were not attending to, over the background noise of many other voices. The foundational experiments were conducted by the British cognitive psychologist Colin Cherry. In 1953, Cherry published a paper describing what happened when he played two different spoken messages simultaneously, one to each ear of a participant wearing headphones. This is called a dichotic listening paradigm. The participant was instructed to attend to the message coming in one ear and ignore the message coming into the other ear, tracking the attended message by repeating it back aloud. A technique called shadowing. Cherry found that participants were, indeed, largely successful at shadowing the attended message while ignoring the other. They could tell you what the attended message said. But when asked about the ignored message, the one in the unattended ear, they recalled almost nothing. They could tell you whether it was a male or female voice. They could tell you it was in English rather than another language. But they couldn't tell you what it said. With one exception. Neville Morey, extending Cherry's work in 1959, inserted participants' own names into the ignored channel, the one they were explicitly trying not to listen to. Approximately a third of participants detected their own name in the ignored channel, despite actively directing their attention elsewhere. 1 in 3 people, hearing their own name in a message they were deliberately ignoring, still noticed it. 1 in 3. In the context of dichotic listening research, that's a remarkable breakthrough for a supposedly ignored signal. The cognitive architecture behind this is now reasonably well understood. The brain doesn't process the attended and ignored channels by simply blocking the ignored channel completely. It processes both, just at different depths with different allocation of attentional resources. The ignored channel is processed up to a certain level, and most of that processing doesn't reach full conscious awareness. But there are certain kinds of stimuli that have enough inherent priority, enough built-in significance, that they can commandeer attention even from the ignored channel. Your own name is one of them. What this means at the neural level is that the brain maintains a low-level monitoring process for your own name even when conscious attention is fully directed elsewhere. Something in the processing architecture is always, in some layer, listening for that pattern. And when it detects a pattern match, when something in the incoming acoustic stream matches the template for your name, it triggers an attention reorientation response. A kind of neural alarm that says, something just happened that you probably need to attend to. This is supported by neuroimaging evidence. Studies using fMRI and EEG have consistently found that hearing your own name activates a distinctive network of brain regions that is not activated by other names or other words with equivalent acoustic complexity. The medial prefrontal cortex, one of the regions most consistently associated with self-referential processing, with thinking about yourself with the neural machinery of identity, responds to your own name with particular vigor. So does the angular gyrus, a region associated with integrating self-relevant information across modalities. So does the right temporoparietal junction, which is associated with directing attention to personally significant information. So does the anterior cingulate cortex, which is involved in detecting things that are personally relevant and deciding how much attention they deserve. Hearing your name activates the brain's self-system. It activates the neural architecture of identity, of personal relevance, of this matters to me. And it does so faster and more robustly than almost any other auditory stimulus. Now add the Portis finding that we discussed earlier. This preferential processing of your own name, this enhanced neural response, is preserved even during sleep. Even when you are deeply resting, the amygdala and prefrontal regions respond more strongly to your name than to other names. The sleeping brain's priority filter keeps your name near the top of the list. Hold all of this in mind as we move forward. Your brain has been trained across your entire life to treat your name as a high-priority signal. It processes your name especially during wakefulness, filtering it through the self-relevant networks before doing the same for other words. It maintains vigilance for your name even in the supposedly ignored channel of attention. And it continues to respond to your name with elevated activity even during sleep. All of this is the soil in which the hypnagogic experience grows. Because now we can ask the real question. When the drowsing, generative, boundary-dissolving brain of hypnagogia starts producing its own internal sounds, drawing from its deepest acoustic libraries, running its most familiar patterns, what is it most primed to generate? The threat detective, how your amygdala guards your name. Let's go deeper, because there's a structure in your brain that plays a particularly important role in what happens to the sound of your name during sleep, and understanding it adds another layer to everything we've been building. Deep inside the medial temporal lobe, tucked close to the hippocampus, the brain's indexer of memory, sits a small, almond-shaped cluster of nuclei called the amygdala. One on each side, mirroring each other across the midline. The amygdala is one of the oldest structures in the mammalian brain from an evolutionary standpoint. Versions of it predate the elaborate cortical architecture that makes the human brain distinctive by hundreds of millions of years. Its core function is threat detection and emotional salience processing. Scanning incoming information for anything that might be dangerous, unexpected, or personally important, and generating the neural and physiological responses appropriate to that information. The amygdala has a famous fast-track connection to the thalamus that bypasses the cortex entirely. Most sensory information in the brain takes what researchers call the high road. traveling through the thalamus and into the sensory cortex, where it is processed in detail before any response is generated. This is the slower, more thorough route, the route that allows for conscious analysis. But there is also a low road, a direct projection from the thalamus to the amygdala that carries a coarser, faster signal, allowing the amygdala to initiate a response before the cortex has even had a chance to process what the stimulus was. This is why you flinch before you know what you flinched from, why your heart starts pounding before your conscious mind has determined whether the shadow was a threat or a coat on a door, why the reflexive, physiological alarm can precede rational analysis by hundreds of milliseconds. The amygdala acts first. The cortex catches up. During wakefulness, this amygdala response is kept in context and proportion by strong connections from the prefrontal cortex, specifically the ventromedial and orbital prefrontal regions, which have dense inhibitory projections to the amygdala. These prefrontal areas serve as the amygdala's regulator, its fact-checker. When the amygdala fires a threat response, the prefrontal cortex can assess the situation and, if the threat is illusory or manageable, send the signal that says, "Stand down." This prefrontal modulation is a major component of what we call emotional regulation. It is why, as an adult, you can walk past a dark alleyway without dissolving into terror. The amygdala might register it, but the prefrontal cortex steps in to contextualize. As you fall asleep, this balance shifts. The prefrontal cortex, which is metabolically demanding and heavily dependent on proper rest to maintain its function, is one of the first regions to begin stepping back as sleep onset occurs. Its ability to modulate the amygdala weakens. The regulator starts to relax its grip on the sentinel. The amygdala, meanwhile, does not go to sleep as quickly or as completely. It maintains its vigilance function for longer. It remains sensitive to incoming signals, particularly signals that have a history of requiring a response. And it continues to do what it always does: scanning, flagging, generating responses to things it perceives as personally significant. Now consider what your name is from the amygdala's perspective. Your name is the most consistently socially salient sound in your personal acoustic history. Every single time you have heard your name in your life, there was an implicit social demand attached to it. Someone was directing attention at you. Someone expected a response. The social consequence of ignoring your name being called, of not responding, has, across your entire life, ranged from mildly awkward to potentially serious. Your name being called urgently by someone whose voice carries alarm, that's one of the most alerting sounds the human auditory system can encounter. Even your name called gently still means someone sees you, someone has something to say to you, someone needs you to engage. The amygdala has been learning this association across your whole life. It has been calibrated by experience and repetition and emotional significance to treat the sound pattern of your name as a high-priority alerting signal. In the hypnagogic state, with the prefrontal cortex stepping back from its regulatory role and the amygdala still running its ancient vigilance program, the threshold for flagging something as your name can become lower than it is during fully alert wakefulness. The amygdala, without its usual cortical oversight, is running a somewhat more trigger-happy version of its name detection algorithm. It's looking harder for the pattern, with less top-down restraint checking its conclusions. And simultaneously, the brain is generating internal content. The early fragments of dreams, the spontaneous activations of acoustic memory, the noise of a brain that is still technically running while shutting down. and running all of it past this heightened, underregulated threat detector. Sometimes, in those conditions, the amygdala fires on a false positive. It detects a pattern in the internal noise that matches, closely enough, the template for your name being called. And when it does, it initiates the response that it was built to initiate: a surge of alerting, a pull toward wakefulness, an almost physical sensation of urgency. And you hear your name, not because someone said it, but because the brain's oldest and most vigilant threat detection system told you it did. The jolt that follows, that small, involuntary startle, is the amygdala's alarm bell sounding. It is physiological evidence that something deep and old in your brain's architecture flagged a personally significant signal and routed it directly to your attention, the way it has been built to do for most of the history of your species. Understanding this doesn't diminish the experience, contextualizes it. The voice you heard before sleep was the output of a system that has, across millions of years of evolution and across every day of your personal life, been shaped to find exactly that signal and make sure you don't miss it. Even when there's nothing there, the architecture fires. Because the cost of missing a real call across evolutionary history was always potentially greater than the cost of a false alarm. The brain that predicts what it hears, predictive processing, and the voice in the dark. We have one more piece to add to this picture, and it is perhaps the most elegant piece, the one that ties everything together and explains not just why the brain generates voices, but why those voices are so clear, so specific, and so compellingly real in the moment before sleep. The piece comes from a framework called predictive processing, a theory of how the brain works that has gathered enormous scientific attention and evidence over the past 2 decades, and that has fundamentally changed the way neuroscientists think about perception. Here is the core idea, and I want to take a moment to lay it out carefully because it's both important and counterintuitive. Your brain is not a passive receiver of information from the world. The traditional model of perception: stimulus comes in, brain processes it, perception results, is not quite how things work. The more accurate model, supported by an extensive body of experimental and computational evidence, is this: the brain is an active prediction machine. At every moment, it is generating top-down predictions about what it expects to encounter in the sensory world, based on its experience, its current context, its model of how the world usually is. These predictions are sent downward through the neural hierarchy, from higher cortical areas down to the sensory areas, and they influence what those sensory areas process and report. When actual sensory input arrives, the brain compares it to its prediction. If the prediction matches the input reasonably well, the mismatch is small, and the brain doesn't need to update much. Processing is efficient. The world is confirming what you expected. When the input differs significantly from the prediction, when something unexpected arrives, the brain generates what researchers call a prediction error. A signal that says, "My model was wrong. Something different from what I expected is happening." This error signal travels upward through the hierarchy, prompting the higher areas to update their model, to revise the prediction, to incorporate the new information. The elegant and initially surprising implication of this framework is that your conscious perceptual experience is largely a construction. What you experience is predominantly the brain's best prediction, continuously refined by sensory evidence. The rich, detailed, vivid experience of the world that you have when you're awake is not a direct reading of incoming sensory data. It is the brain's current best model of what the world is like, being continuously updated by data that mostly confirms it. This is why optical illusions work. This is why the dress appeared different colors to different people. This is why you can mishear a word in a noisy environment and be completely convinced you heard something different from what was actually said. The prediction system can be fooled. The brain's model can diverge from actual reality, and the divergence is not always immediately detected or corrected. Now apply this to the hypnagogic state, to the brain in N1 sleep, drifting in the theta haze of the sleep threshold. During wakefulness, the prediction system is kept honest. Sensory data is coming in continuously, richly, at high quality. Every time the brain's prediction diverges from reality, the mismatch signal is strong and clear, and the model is corrected. The prediction system is running against a firm floor of actual sensory experience. In N1 sleep, that floor becomes thinner. The thalamic gate is closing, reducing the flow of external sensory information to the cortex. The incoming data is sparser, lower quality, and more ambiguous. There is less sensory evidence available to correct the predictions. The ratio of prediction to evidence shifts, with more prediction and less evidence. In that environment, the predictions begin to dominate. The brain starts to experience its own predictions, its own internal models of what might be there, with fewer external constraints to push back against them. The internal model gains a kind of perceptual presence that it normally cannot achieve during wakefulness because the data is too rich to allow it. This is the fundamental mechanism of all hypnagogic hallucinations. The brain is experiencing its own predictions in the absence of the strong sensory signal that would normally correct them. The mental imagery that arises before sleep, the faces, the landscapes, the fragments of scene, are not random noise. They are the brain's predictions becoming visible, felt, real, in the absence of sufficient external signal to redirect them. And what does the auditory prediction system predict in the drowsy, self-referential, amygdala-vigilant state of hypnagogia? Predicts the sounds it has most often heard. The sounds it has the richest and deepest models of. The sounds it has been most consistently taught to anticipate, to prioritize, to respond to. Voice, first of all. The human voice is the most intensely learned and most elaborately modeled sound in the human brain. We are a social species, and the voice has been the primary carrier of social information for our entire evolutionary history. The neural circuitry devoted to processing speech and voice, the regions of the superior temporal gyrus, the language networks, the social voice areas, is some of the most extensively developed neural real estate in the human brain. The brain's internal model of what speech sounds like, of what voices sound like, is extraordinarily detailed and richly specified. In hypnagogia, with the external data thinning and the internal predictions gaining influence, the voice model starts to surface. The brain generates the auditory experience of voice from its own internal model, and because the model is so detailed, the result can be startlingly clear. But not just any voice. The voices that are most deeply modeled. The voices that the brain's experience and emotional history have most thoroughly specified. The voices of people who matter to you. People who have spoken to you many times. People whose voices carry emotional significance. People who have been part of the acoustic landscape of your most important experiences. And those voices, what have they most consistently said to you? What is the single utterance that appears in every emotional register, in every social context, across every year of your life, spoken by every person who has ever mattered to you? Your name. The predictive auditory system, running without sufficient external data to constrain it, generates the most deeply learned, most strongly predicted, most emotionally significant sound in its entire library. And you hear it, clearly, as if someone is in the room, because as far as the prediction system is concerned, as far as the diminished reality monitoring of the hypnagogic brain can determine, something might be, when the volume is turned up, sleep deprivation, stress, and the amplified experience. You may have noticed, if you've paid attention to these experiences across different periods of your life, that they vary. There are stretches of time when you never hear anything before sleep, when the transition is smooth and quiet and uneventful. And there are other stretches, and you probably know exactly what these stretches feel like, when the experiences are more frequent, more vivid, more startling, more insistent. Those stretches have a consistent profile. They are times of high stress, of inadequate sleep, of fatigue accumulated over days or weeks. The periods when you are, in the language of ordinary life, running on less than you need. This correlation is real, and the neuroscience behind it is specific and instructive. Let's start with sleep deprivation, because its effects on perception are among the most thoroughly documented findings in all of sleep science. The relationship between insufficient sleep and hallucinations is not obscure or specialized knowledge. It has been studied systematically, replicated across multiple laboratories, and is now part of the established scientific understanding of what sleep deprivation does to the human brain. The progression follows a fairly predictable timeline. After one night of no sleep, roughly 24 hours of extended wakefulness, the first perceptual disturbances begin to appear in otherwise healthy individuals. These are typically subtle: visual distortions at the periphery of vision, mild misinterpretations of ambiguous stimuli, difficulty distinguishing ambiguous sounds from silence. They are easy to dismiss. Most people who experience them after one sleepless night don't flag them as hallucinations. They just think they're tired. After 36 to 48 hours without sleep, the experiences become more pronounced. Images appear in peripheral vision. Sounds are heard that don't exist. Familiar objects take on unfamiliar qualities. The boundary between what is perceived and what is imagined begins to soften in ways that become harder to ignore. After 72 hours, 3 days without sleep, complex multimodal hallucinations become common in otherwise healthy individuals. People see and hear things that are not there. They have conversations with people who are not present. The perceptual system begins to generate content that has no correspondence with external reality, and the reality monitoring systems that would normally catch and correct this are too impaired to perform their function. This was systematically documented in review research published in journals including current psychiatry reports. The finding is consistent across multiple studies. Extended sleep deprivation in people with no history of mental illness, no prior hallucinatory experiences, no neurological conditions. Extended sleep deprivation reliably produces hallucinations. The brain does not need to be unusual or damaged to hallucinate. It needs primarily to be sufficiently deprived of sleep. Why does this happen? What is the neural mechanism? At least 3 overlapping mechanisms contribute. First, the thalamic gating system becomes less effective when the brain is sleep deprived. The TRN neurons that normally generate the inhibitory gating signals during sleep are themselves fatigued and operating at reduced capacity when sleep has been inadequate. Their firing is less precise. Their inhibitory signals are less well-timed. The gating function becomes messier, less controlled. meaning that the filtering of incoming sensory signals becomes less precise and more noise, more ambiguous information passes through to the cortex without being appropriately suppressed. Second, the prefrontal cortex, which is the brain's primary system for reality monitoring, for flagging internally generated content as internal, for maintaining the distinction between self-generated and externally originated experience, is exquisitely sensitive to sleep deprivation. Among all the brain regions that are studied in relation to insufficient sleep, the prefrontal cortex shows some of the earliest and most significant functional decline. Its glucose metabolism drops. Its blood flow decreases. Its connections to other regions become less functional. The prefrontal cortex, without adequate sleep, is not doing its job properly. And one of the jobs it does that is most directly relevant to us is monitoring the origins of conscious content. During normal wakefulness, the prefrontal cortex helps the brain tag its own internally generated representations as internal, keeps track of the difference between "I thought of that" and "I heard that." This source monitoring function is one of the things that breaks down most specifically during sleep deprivation and during hypnagogia both. And when it breaks down, internally generated content is not correctly tagged as internal. It surfaces as something that feels like it came from outside. Third, the neurochemical balance of the awake and sleeping brain is disrupted by insufficient sleep in ways that specifically affect perception. Dopamine signaling, which plays complex roles in attention, motivation, and the tagging of stimuli as significant, is altered. Cholinergic tone. The acetylcholine-mediated arousal system that contributes to the vivid quality of experience shifts in ways that parallel the chemistry of dreaming, even during wakefulness. The brain's neurotransmitter landscape begins to drift towards something that resembles the chemistry of a sleeping or dreaming brain even while the person is still awake. The sensory-generating, vivid experience-producing chemistry of sleep starts to leak into waking. For someone who is sleep-deprived and drifting into N1 sleep, this means entering the hypnagogic state from a starting point of already weakened gates, already diminished reality monitoring, and already shifted neurochemistry. The hypnagogic experience is more intense. The predictions are more vivid. The boundary between internal and external is already thin before N1 even begins. The voices, when they come, are louder and more compelling. Stress operates through overlapping but distinct mechanisms. When you are under significant psychological stress, the kind that sits with you, that runs in the background even when you're not consciously thinking about it, that has your nervous system in a state of elevated preparedness, the hypothalamic pituitary adrenal axis is activated. Cortisol levels are elevated, particularly in the evenings when they would normally be at their lowest. The sympathetic nervous system maintains a background tone of arousal that it should, by bedtime, be releasing. Cortisol elevation in the evening interferes with sleep onset specifically. It makes the transition from wakefulness to N1, that threshold we've spent so much of tonight exploring, more abrupt, more turbulent, and more likely to produce vivid hypnagogic experiences. When the body and nervous system are still running at stress response levels as you try to fall asleep, the thalamic gating doesn't proceed as smoothly. The amygdala, primed by the elevated stress hormones, is running at even higher sensitivity than usual. The prefrontal cortex's ability to contextualize and regulate the amygdala's responses is already taxed from the cognitive demands of managing stress. The combination, elevated amygdala sensitivity, reduced prefrontal modulation, disrupted thalamic gating, and a nervous system that is still partially in stress response mode, creates the ideal neurological conditions for vivid and startling hypnagogic hallucinations. The voice before sleep is not a random occurrence. It is the output of a specific set of neural conditions. And those conditions are most intensely present when the brain and body are most depleted. This is worth knowing practically. The frequency and intensity of these experiences is, in some meaningful sense, a readout of your system's current resource state. Not a diagnostic tool, not a clinical indicator on its own, but a signal worth attending to. When the voice comes more often, when it is more insistent and more startling, it may be your brain, in the most literal neurological sense, telling you that it is overtaxed and under-rested. It is saying your name to get your attention, even if you're the only one there. Across centuries and cultures before science named it, the experience we've been exploring tonight is not new. It did not emerge with modern life or with artificial light or with the particular stresses of contemporary existence. The evidence suggests it is ancient, universal, and has been present in human experience for as long as human beings have been capable of reporting their inner lives. In the classical world, Aristotle, writing in the 4th century BCE, described a state he called the boundary between waking and sleeping in which faint impressions could be perceived with unusual vividness. He noted that in this threshold state, small sensory inputs could generate elaborate apparent perceptions, that a person might see faces or hear voices from stimuli that would, in clear wakefulness, be recognized as trivial. He was describing, with the observational precision characteristic of his best work, the hypnagogic state. And he was noting, more than 2,000 years ago, the exact mechanism we now understand in terms of signal amplification and reduced reality monitoring. When the filtering is reduced, small signals become large experiences. In the ancient Greek and Roman traditions, the state between waking and sleeping was sometimes treated as particularly permeable to divine communication. Certain traditions of dream incubation, the practice of sleeping in a sacred space in order to receive a message or vision from a deity, specifically targeted this threshold state as the moment when divine communication was most likely to reach the human mind. The priests and practitioners of these traditions understood, on some intuitive level, that the threshold was a place where the normal rules of perception didn't apply, where things could be heard and seen that were not accessible to the fully waking mind. Medieval European traditions were similarly attentive to the experiences of the threshold. The figure of the succubus and incubus, the nocturnal visitor who appeared in the night, often experienced with great vividness and emotional intensity, with a quality of absolute physical reality, is now understood to overlap substantially with hypnagogic and sleep paralysis experiences. The particular combination of inability to move, which we now understand as sleep paralysis, the persistence of the atonia muscle paralysis of REM sleep into waking consciousness, vivid visual and auditory hallucinations, and the feeling of a presence in the room corresponds precisely to what we know about the hypnagogic and hypnopompic states from contemporary sleep science. In many indigenous cultural traditions, the hypnagogic threshold was understood as a liminal zone, a space between ordinary reality and another kind of awareness, between the world of the living and the world of the ancestors or spirits. Shamanic traditions across a remarkable range of cultures, from Siberia to the Americas to sub-Saharan Africa, have developed practices specifically designed to access this threshold state deliberately, recognizing it as a zone of unusual perceptual access. The hearing of voices, the seeing of visions, the sensing of presences that don't belong to ordinary waking experience. These were, in these traditions, not aberrations to be explained away but gateways to be cultivated. The specific experience of hearing one's name in the threshold state is documented across many of these cultural frameworks. In numerous traditions, hearing your name spoken by an unseen voice in the night, particularly in the drowsy moment before sleep, was interpreted as meaningful communication from an ancestor, a spirit guide, a deity, or the land itself. The experience was real. The interpretive framework for what it meant varied dramatically, but the experience underneath the interpretation was the same phenomenon that we now understand through EEG readings and fMRI scans and neurochemical analysis. In the Western scientific tradition, the systematic study of these threshold experiences began in the 19th century. The French psychologist Alfred Maury, who suffered from severe migraines and spent considerable time in bed as a result, giving him ample opportunity to observe his own hypnagogic experiences, coined the term hypnagogic in 1848. He documented in meticulous detail the images, sounds, voices, and sensations he experienced in the transition to sleep, and he began to analyze them scientifically rather than supernaturally. He noted the dreamlike quality of the content while observing that it felt, in the moment, distinctly external. Frederick Myers, a British scholar and one of the founders of the Society for Psychical Research, added the term hypnopompic in 1904, coined to describe the equivalent experiences occurring on the threshold of waking up, rather than falling asleep. Myers was interested in these experiences from a psychical research perspective, but his descriptions were careful and consistent with what contemporary neuroscience describes. The psychoanalytic tradition took up the hypnagogic state as a subject of intense interest in the early 20th century. Herbert Silberer, a contemporary of Sigmund Freud, described a phenomenon he called autosymbolism, the tendency of the hypnagogic mind to translate abstract thoughts into concrete perceptual images and sounds. If he was drowsing while thinking about a complex philosophical problem, the problem might surface as a visual scene or a heard phrase rather than as a coherent abstract thought. His observations anticipate what contemporary predictive processing theory describes: the brain converting high-level representational content into lower-level perceptual simulation. What is remarkable about reading all of these accounts, from Aristotle to Maury to contemporary sleep scientists, is how consistent the descriptions are. The voice that feels completely real, the name spoken into the quiet, the startling quality of it, and the subsequent realization that the room is empty. These details are reproduced across cultures and across centuries with a fidelity that tells us something important. We are dealing with a universal feature of human neurology, something that emerges reliably from the way human brains are built, not from any particular cultural condition or historical moment. The experience is the same in ancient Athens, in medieval Europe, in contemporary bedrooms where someone is listening to a science sleep channel in the small hours of the night. The brain, in the threshold of sleep, has always done this, and the sound it has always most often made, across every culture and every era for which we have records, is the sound of a voice calling to the sleeper, calling them by name, the signature of sleep, N2, spindles, and the protecting brain. As sleep deepens past N1, as the theta waves of the hypnagogic state give way to the more organized patterns of stage N2, something happens in the EEG that is one of the most studied and most discussed features of human sleep. Something appears that wasn't there before. Brief, rhythmic, elegant bursts of electrical activity that seem to emerge out of the background like tiny storms and then subside, lasting 1 to 2 seconds each, appearing somewhere between 5 and 15 times per minute. These are sleep spindles, and they are, in some ways, the brain's most elegant example of doing two things at once that seem initially contradictory: protecting sleep from the outside world while simultaneously doing some of the most important processing work of the night. Sleep spindles oscillate at 11 to 15 Hz, faster than the theta waves of N1 sleep, slower than the beta waves of waking. They are generated by the interaction between the thalamic reticular nucleus and the thalamocortical relay circuits, the same TRN-mediated gating mechanism we discussed earlier, now operating in a more regular cyclical way. Each spindle represents a burst of coordinated inhibitory activity from the TRN, briefly and rhythmically suppressing the relay neurons and creating the oscillating, wave-like pattern that shows up in the EEG. From a sensory gating perspective, sleep spindles do what you might expect. Research measuring arousal thresholds, how much stimulation it takes to wake someone from different sleep stages, has consistently found that N2, with its abundant spindles, is harder to rouse from than N1. The spindles are actively protecting sleep. They are the thalamic gate doing its job in a rhythmic, systematic way. But here is what is beautiful about them. They are not just protective. They are also productive. Sleep spindles are one of the key mechanisms of memory consolidation during sleep. Research by Robert Stickgold at Harvard, and by many others working in the field of sleep and memory, has established that sleep spindles are closely linked to the consolidation of new information acquired during the waking day, particularly procedural memories, how to do things, but also declarative memories, facts and events. Spindles appear to be one of the mechanisms by which the hippocampus, which stores newly acquired memories in a temporary and fragile form, communicates with the neocortex, where long-term memories are eventually stored. The rhythmic thalamocortical oscillations of spindles help synchronize these two regions, facilitating the transfer and consolidation of information. The brain is not idle during sleep spindles. It is doing some of the most important organizational work of the sleep period, sorting, strengthening, and filing the day's experience. And crucially for our story tonight, sleep spindles have a specific relationship with auditory processing that is more nuanced than simple suppression. Research published in PNAS Nexus in 2024, examining how spindles affect the brain's responses to sounds, found evidence for a two-phase relationship. During spindles, responses to neutral or background sounds are suppressed, the gating function. But around spindles, in the moments before and after each spindle burst, the auditory system can actually show periods of increased responsiveness, as if the gating and ungating of the thalamic circuit creates windows of slightly elevated auditory access. This means that even in N2 sleep, even with spindles actively protecting sleep from sensory disruption, the auditory system is not uniformly or continuously blocked. There are rhythmic windows, moments between spindle bursts, when sounds can reach the cortex with somewhat less resistance. And again, the sounds that clear these windows most easily are the sounds that the system has been calibrated to treat as personally significant. The sounds that the amygdala and self-referential networks flag as high priority. The sounds that have, over a lifetime, been consistently linked with the need to respond. Your name in a known voice is exactly such a sound. Even in stage N2, even with spindles protecting sleep, your name continues to penetrate the sleeping brain's defenses. It continues to activate the amygdala. It continues to trigger the self-referential processing networks. It continues in the measurable language of neural responses to matter. This is part of why the hypnagogic experience of hearing your name so often has the quality of pulling you back from deep sleep rather than just arising in the very light drowsiness of early N1. Because the sound, real or internally generated, has enough personal significance to clear the filters not just of N1 but of the early stages of N2. The voice can follow you deeper into sleep before it releases you. Understanding sleep spindles also helps us appreciate something else about the hypnagogic experience. Spindles represent the brain in a state of transition. Not yet in the deep, slow-wave sleep of N3, where the delta waves roll in great, sweeping tides and genuine unconsciousness descends, but no longer in the barely sleeping threshold of N1 where the worlds blur most easily. N2 is the most abundant stage of sleep in terms of sheer time. It constitutes roughly 50% of the total sleep period in adults. It is the middle country of sleep, and it is a country where the brain is doing complex, organized work. Hypnagogic experiences most commonly arise in N1, but they can extend into early N2, particularly when they are intense enough or when the system generating them, the amygdala, the auditory vigilance system, the self-referential network, is running at elevated sensitivity due to stress or fatigue. The voice that seems to come just as you were really starting to settle, deeper than you'd thought. That's the auditory vigilance system reaching past the boundary of N1, carrying the signal deeper than it would in a quieter nervous system. Who you are at the edge of sleep, the default mode network. There is one more piece of this story, one more neural network to introduce, because understanding it adds something specific and irreplaceable to the picture. It helps explain not just why the brain generates voices, and not just why those voices say your name, but why the whole hypnagogic experience has the particular quality of intimacy and self-reference that makes it feel different from random noise. Why it feels, even when startling, like something that is about you. The default mode network, or DMN. The default mode network is a set of brain regions that activate together specifically when you are not engaged in a task directed at the external world. When you are sitting quietly, not attending to anything in particular, not being asked to do anything. When the mind is at rest from external demands, this network becomes more active, not less. It is the network of the internal life, of self-referential thought, of mental time travel, remembering the past and imagining the future, of thinking about other people's minds and about your own, of the ongoing narrative of who you are. The key nodes of the DMN include the medial prefrontal cortex, the region most consistently associated with thinking about yourself, your values, your traits, your identity. The posterior cingulate cortex, involved in self-referential processing and in integrating memories. The angular gyrus, which connects language and memory in ways related to autobiographical understanding. The hippocampus and surrounding structures, which store the narrative thread of your life. These regions are connected to each other in a consistent, reproducible pattern that is visible in resting state fMRI, and they are active whenever the mind turns inward. The DMN was initially somewhat overlooked in neuroscience because early neuroimaging research was focused on what the brain does during specific tasks, not on what it does when not doing tasks. But when researchers began to look systematically at what happens during rest, during the mind's unstructured time, the DMN's activity was impossible to ignore. It was doing something consistent and organized and energetically expensive. The question was what? The current understanding is that the DMN is the brain's internal narrative engine. It constructs and maintains the self, processes autobiographical memories. It imagines possible futures. It models other people's perspectives. It generates the internal monologue, the inner voice that accompanies your experience of being you. The DMN is, in a meaningful sense, the network of you. What happens to the DMN as you fall asleep? Research using resting state fMRI, which measures the correlations of activity among different brain regions over time, has tracked DMN connectivity across the wake-to-sleep transition. The finding is complex and initially counterintuitive. In the earliest moments of sleep onset, in N1 sleep, the connectivity within the DMN actually increases relative to quiet wakefulness. The internal processing ramps up, not down. The narrative self becomes more active in the first moments of sleep, not less. This makes a certain intuitive sense. N1 sleep is when thoughts become more associative, more emotionally colored, more loosely connected. When the strict logical organization of waking thought relaxes and the mind begins to wander through territory it hasn't visited during the structured demands of the day. The DMN, which governs exactly this kind of internally directed, associatively organized, self-referential processing, flourishes in this early territory. As sleep deepens into N2 and then into N3, the DMN's connectivity begins to dissolve. The anterior and posterior nodes, which need to work together closely to generate the coherent self-referential narratives of the default mode, begin to decouple. The network's characteristic coherence breaks apart. The self in deep sleep is no longer generating its story. The narrative is on pause. But in N1, in hypnagogia, in the very territory where the voice before sleep appears, the DMN is active. The self-generating, identity-maintaining, self-referential engine of the brain is running at full capacity, maybe more than full, and it is running without the external constraints and task demands that normally channel and structure its activity during waking. In this state, the DMN draws on its richest material, the most deeply stored, most emotionally significant, most self-defining content it holds, and it generates experience. The loose, associative, emotionally alive experience of early sleep from that material. What is the most self-defining sound? What is the auditory content that has been most consistently associated across your entire life with your existence as a person known to others? What sound has the deepest roots in the medial prefrontal cortex's representation of yourself? Your name. The sound of being called by someone who knows you, the sound that has always meant, you are here, you exist, and you matter. The DMN, active in early sleep, reaches into its deepest material and surfaces the most fundamental evidence it has for your existence. It runs the pattern that it has always used to anchor the self in social reality. And in the generative, reality monitor-free, porous state of hypnagogia, that pattern surfaces not as a thought but as a perception, not as a memory but as a sound, not as something you remember hearing but as something you are hearing right now in the room. Your name, spoken into the quiet, by a voice that knows you. What the experience means, reflection and practical understanding. We have covered a great deal of ground tonight. Let's rest in it for a moment before we bring it all together. We started with the experience itself, that sharp, clear, startling voice in the quiet before sleep. We followed it through the neurological architecture of sleep onset, the alpha to theta transition, the permeable boundary of N1 hypnagogia, the generative state where internal and external blur. We explored the auditory system that never fully stops listening. The primary auditory cortex that responds to sounds with only modest reduction during sleep, the thalamic gating system that filters selectively rather than completely, the amygdala's express lane that keeps personal significance flagged even as consciousness retreats. We mapped the special neural status of your own name, the self-referential networks, the cocktail party detection mechanism, the lifetime of learning that has made your name the most overlearned and most neurologically privileged sound in your entire acoustic experience. We looked at how the predictive processing system generates sounds from internal models when external data becomes too sparse to constrain it. We examined how stress and sleep deprivation intensify and amplify these experiences, lowering the gating, diminishing the reality monitoring, heightening the amygdala's already elevated vigilance. We traced the experience through history and across cultures, finding it everywhere that human beings have been lying down in the dark and crossing into sleep. And we found, at the center of it all, the DMN, the brain's internal narrative self, reaching into its deepest material and speaking the most important word it knows. What do we do with all of this? The first thing, and perhaps the most important, is simply to stop being afraid of it. If you have been carrying some background worry about these experiences, some quiet concern that hearing a voice before sleep means something is wrong with you, that it's a symptom of something, that it's a sign of deteriorating mental health or sleep quality or sanity, let that concern go. The experience is normal. It is common. It is experienced by a majority of people at some point in their lives, and in many people it occurs regularly without any indication of any underlying problem whatsoever. It is not a symptom of psychosis. The auditory hallucinations associated with conditions like schizophrenia are phenomenologically distinct from hypnagogic voices. They occur during full wakefulness. They persist across many different contexts. They are often accompanied by other features like delusional thinking about who the voices belong to or what they want. The hypnagogic voice is context-specific. It occurs only in the very specific neurological state of sleep onset. It is brief. It often has a quality of suddenly startling you awake, which is the amygdala's response to flagging a personally significant signal. And it doesn't persist into the rest of the night or into the next day. These features clearly distinguish it from the auditory hallucinations of psychotic conditions. The second thing is to pay attention to the pattern. Not anxiously, not obsessively, but thoughtfully. The frequency and intensity of hypnagogic experiences does tend to correlate meaningfully with the state of the nervous system. If you notice that you've been hearing your name before sleep every night for a week, and that the experiences are more vivid and more startling than usual, that's worth taking as a signal. Not a medical alarm, but an informational signal. Your nervous system may be telling you something about its current resource state. Are you sleeping enough? Are you managing stress? Are there things you're not addressing that are keeping your amygdala running at elevated sensitivity? The voice before sleep is sometimes the brain's way of making those questions audible. Third, if you are curious about these experiences, and I hope after tonight you are curious rather than concerned, there is actually a long tradition of people who have made productive use of the hypnagogic state rather than simply being surprised by it. Artists, writers, and scientists across history have developed techniques for hovering in the threshold state deliberately, using the generative freedom of hypnagogia as creative fuel. Thomas Edison is often cited as someone who used the hypnagogic threshold deliberately, napping in a chair while holding steel balls in his hands, so that when he drifted towards sleep, the balls would drop, the noise would wake him, and he could record the ideas that had arisen in the threshold before they dissolved. Salvador Dali reportedly used a similar technique, calling it slumber with a key. Many artists and writers have described the hypnagogic state as a source of unusually vivid and unexpected imagery, precisely because the normal censoring and editing functions of the rational mind are stepped back and the generative machinery runs more freely. The threshold is a creative space, not just a startling one. Fourth, and perhaps most fundamentally, consider the beauty of what you've learned tonight. The voice before sleep is not a glitch. It is not an error. It is not evidence of something wrong. It is the output of some of the most sophisticated and most ancient neural architecture in the human brain. The auditory vigilance system that kept your ancestors alive through the long nights of evolutionary history, the self-referential processing that defines your identity, the predictive modeling that constructs your experience of the world, the social processing that makes you, at the deepest biological level, a creature that is embedded in relationships with others. All of this machinery, all of this extraordinary complexity, runs in the few minutes before you fall asleep. And what it produces, from all of that complexity, is the sound of someone calling your name. The most personally significant sound in your acoustic world. The sound that has always meant, you are here and someone knows it. There is something genuinely moving in that, if you let yourself feel it. The deepening quiet moving toward real sleep. We've been in this conversation for a long time now. And as we've been talking, if you've been listening in the dark, if you've been following this while lying in your bed, your eyes closed, you're breathing slower than when we began, then something has probably been happening to you even as we talked about the science of it happening. Your brain has been crossing the same threshold we've been describing. The alpha waves that were rolling through your EEG when you first lay down have been slowing. The theta waves of early N1 sleep have been appearing in the records, if you had the electrodes to record them. Your thalamic gate has been beginning its work. The TRN neurons have been gently increasing their inhibitory firing, and the sensory world, this voice, these words, the sounds of the room around you, has been reaching your cortex with slightly less force than it had an hour ago. Your amygdala is still listening, but the prefrontal cortex that mediates its urgency is softening. The vigilance is still there, but it has a different quality. Less acute, more diffuse, less able to pull you sharply into alertness. And your default mode network, which has been quietly active beneath the science and the explanations, has been reaching into its own material, generating the loose, associative, emotionally colored fragments that constitute the earliest stirrings of the internal world that sleep will eventually fill with dreams. The boundary between what you're hearing and what your brain is generating has been getting thinner all this time. Not in any alarming way. In the way it is supposed to get thinner. In the way that is simply, biologically, the beginning of sleep. And if, in the next few minutes or the next few seconds, you hear something that you can't quite source, a word or a phrase or a name spoken into the quiet, I hope that what you feel is not alarm but recognition. Recognition of what's happening. Recognition of your brain doing its ancient, elaborate, sophisticated, beautiful work. Recognition of the thalamic gate closing, the prediction system surfacing its deepest material, the amygdala running its last check, the self-referential networks reaching for the most fundamental sound they know. Recognition that the voice before sleep is not something to be startled from but something to be understood. And understanding it, having done the work of understanding it tonight, is a kind of gift to yourself, because now the experience belongs to you differently. It is not strange anymore. It is yours. You know what it is. You know why it happens. You know the extraordinary neural machinery behind it. And you can let it happen without fear. Let the voice come if it comes. Let the threshold do what the threshold does. Let your brain cross into sleep the way it always crosses. By generating its own version of the sound it knows best, running its most personal program one more time in the quiet, saying the word that means you and then letting go. Soft landing. Tonight we went deep. We traveled from that familiar, slightly startling experience of your name spoken in the quiet, through the theta waves of N1 sleep, through the thalamic gate and its deliberate gaps, through the lifetime of learning that makes your name the most neurologically special sound you've ever heard. We followed the auditory cortex that never quite stops working, the amygdala's ancient vigilance, the predictive processing system that generates the sounds it most expects to hear. We found these experiences in ancient philosophy and in medieval superstition and in Victorian drawing rooms and in contemporary neuroscience laboratories with intracranial electrodes. And we arrived at the same place each time. The human brain in the threshold of sleep doing what it has always done. Saying your name. If this journey reached you, if it settled something that felt unsettled, or explained something that felt inexplicable, or simply gave you something interesting to hold in the quiet before sleep, please consider sharing it with someone who might feel the same. These are the kinds of conversations that are best had in the dark, at the end of the day, when the science and the experience can speak to each other without the noise of the waking world getting in the way. And if you're new here, if this is your first night with Deep Science Sleep, welcome. This is what we do here. We take the science of the sleeping brain seriously, and we explore it together gently and thoroughly and with genuine curiosity. New episodes explore the extraordinary territory of the night in the same spirit. Intimate, careful, and always following the evidence wherever it leads. The next time you hear your name in the dark, you'll know what it is. And maybe, instead of being startled back into the world, you'll smile. Just slightly, and let the threshold do its work. Sleep well. You've earned it. If this video was something you'll come back to, the like button is right there. It genuinely helps this kind of science content reach more people who are lying in the dark wondering the same things you were. Subscribe to Deep Science Sleep for new episodes, and I'll be here the next time you need someone to meet you at the edge of sleep. Asterisk.